Now we want to look at some general problem-solving guidelines for two-dimensional kinematics motion. In these slides, we will illustrate a process. Now, if you think about it, if you want to learn something well, who do you go to? Well, you want to learn something, you go to an expert. You go to someone who is proficient and fluent in whatever it is you're trying to learn. And so that's the best way to learn. We all learn that way. You learn by watching people. You learn how to ride a bike. You learn by trial and error, even though someone showed you something. And over time, you became an expert in that skill. And so we really just want to develop our skills through practice and through modeling of those skills by watching how experts do that. So let's look at how we would go about solving physics problems and try to build our proficiency in solving these types of problems. First of all, in all kinematics problems, you're trying to answer a question. Let's face it, you're trying to find out something about this motion. The question might be, how high does it go? How far does it travel? How much time does it take? How fast is it going when it reaches a particular point? So those would be common questions. And as you find the question in any problem, try to find the relevant statement in that question. If the question is how much time does it take, then you're being asked to find the time. How far does it travel? You're being asked to find some distance, perhaps the distance x in the horizontal direction. Or how high does it go is what is the value of y? So how fast is it going when it reaches its peak? What is its value of its velocity at that point? So you're looking at your problem and you're trying to break it into pieces and find out, well, what do I know and what am I looking for? Some information that you have will allow us to predict the future motion of that object. That's what you're trying to do. Now, with our two-dimensional kinematics problems, we can actually create a list here of the information that you will have and the information you're looking for. After all, if you think about it, it's a fairly select set of things we're talking about. We're only talking about where does the object start and finish, how fast was it moving at the beginning, what is the acceleration involved, and how much time is involved. Based on that, we can fill out from this table, from this list of information, what it is we know, and maybe put a question mark next to what it is we're looking for. Okay? Notice there are two directions. We're tabulating in the x direction and we're tabulating in the y direction the values of the quantities x0, where does the object start, x final, x sub f is x final, where does the object land, v0x, what is the object's initial velocity in the horizontal direction, and ax, what is the object's acceleration in the horizontal direction. Similarly, in the y direction, we have the same quantities. y0, where does it start? y final, where does it end? v0y, how fast was it moving in the vertical direction at the beginning? ay, what is the acceleration in the vertical direction? Okay, so these are the pieces. Next we have our relevant equations. Perhaps you've already surmised that what I'm doing is I'm building the information that goes in my homework template. So the previous slide was a listing of the knowns. And I oftentimes put the unknowns in there. In other words, it might be that I don't know the final position x sub final, but I'll put a question mark next to that, and that'll indicate to me, okay, that's something that I'm looking for. So now we're into the relevant equations box of our homework template. Well, you don't need all these equations, obviously. It depends on what you're solving for. So you might pick the ones that are relevant. If the problem is asking for how far does the ball travel, then, and it's thrown up and it comes down and lands on the ground, and then you might say, okay, I'm looking for the final position x. So I'm going to definitely need an equation that starts with x equals. Okay? And I might need to know the time, so I may need to use an equation in the y direction to find out how much time it takes. You'll begin to develop some abilities in this area to decide which equations to use. For instance, let's do this problem. This problem states that we have a long jumper, and he's moving along at a speed of 12 meters per second and launching at that velocity at a 20-degree angle above the horizontal. That means it's the vector velocity represented by this long jumper's motion is a vector pointing upward to the right at an angle of 20 degrees, and the length of that vector is 12 meters per second. And we'd like to know, how long is the jumper in the air before returning to the Earth? Well, notice from the list of information, we're assuming that the coordinate system starts where the long jumper launches. So that's our 0x and 0y starting point. Do we know where the long jumper ends up? Well, we don't. The x sub f value is unknown. Do we know where he jumps, where he lands in the vertical direction? Well, in fact, we do. We could actually write that in there and say the final vertical position of the long jumper is back on the ground. So it would be 0. Can we determine the original velocities in the x and y direction? Well, notice that we can, because the 12 meters per second is the length of the vector v0 inclined at an angle of 20 degrees. So using our trig functions, the sine and cosine trig functions, we find that v0, 12, times the cosine of 20 is our component in the x direction. That comes out to 11.3. And similarly, v0 times the sine of 20 degrees is our component in the y direction. And that works out to 4.1 meters per second. So recall that I said that decomposing or breaking down vectors into its pieces is something that I do in the knowns area of my template, because in reality I do know this information. It's just expressed for me in terms of the length of the vector v0 and the angle, and it needs to be expressed or re-expressed in the form of the components vox and voy. So it's not really any physics there. We're just writing the velocity in a different way, in component form versus the vector notation. We also know that the acceleration in the x direction is 0. In other words, it sounds kind of silly, but the concept is the long jumper is jumping through a vacuum with no air. But that's okay. The vertical acceleration is negative 9.8 meters per second squared. Notice we've included the negative sign in there so that when we plug it into our relevant equations, it shows here as a negative 9.8, indicating it's different in direction from the vertical component of the velocity of 4.1. At any rate, in this area, we are looking at our relevant equations. We've identified that x is 11.3 VOX times t, and that the velocity in the x direction is simply 11.3. That doesn't change because there's no drag on the jumper, because there's no air to create that drag. So the jumper is not slowing down in the forward direction. He's merely launching, slowing down up to the peak of his trajectory, and then falling, speeding up as he comes down. So our x equations are relatively simple. The distance traveled is the velocity times the time of flight, and the velocity is a constant 11.3. Now the question was, how long is the jumper in the air? So that is a calculation of time. How much time does this jumper take in his flight? You'll notice that in this equation here, the x equals 11.3t, we have the time variable there that we're looking for, but we don't have the x. We don't know what that is, do we? So we can't use that equation because we could solve for t, it would be x over 11.3. That doesn't help us because we don't know what x is. But recall that I said that the final position of the jumper was at y equals 0. So in fact, this equation right here, we could put in 0 for y final, and the only variable left in this equation is the time t, as well as t squared, as you can see. And we could solve that equation for the time. And in fact, knowing the time at that point, we could plug that back into our equation here with x and find out where he lands. So there's lots of things, and once we determined the time, we could find out how fast he was moving in the vertical direction when he struck the ground by plugging a time in this equation, and so on. So I hope you notice how breaking this problem down into a process using this template helps you to identify what you know, what you're looking for, what equations are pertinent, and then putting your numbers in these equations and seeing where to go from there. Don't worry if you put some numbers in equations and you come to a dead end like we did here. We put our velocity VOX into this equation here and found that, well, it's a nice equation, x equals 11.3t. It doesn't help us get the time t because we don't know x. And that just means you don't have enough information. However, you have other equations, and you can look to them and ask yourselves, what do I know here? What can I set? For instance, in this case, we set that equal to 0, and it allowed us to solve for the time t. Some of you may be proficient with the spreadsheet programs such as Excel, and you can actually set these problems up in Excel where you can run your time increment here as an index from 0 on down and place your equations on the spreadsheet in the proper format and actually graph the motion and show how it looks. Sometimes this gives you an insight into the motion when you can see it that way. So remember, don't forget to use the template. Follow the procedure of identifying what you know and what you don't know. Label the equations, label all your numbers with a symbol, such as V0 equals 12 meters per second, AY equals negative 9.8 meters per second squared. Put a label with the symbol and units with the numbers. And then collect the equations that are relevant to the motion. Put your values into those equations so you can see where you know numbers and where you don't. And then look and see what equation has the thing I'm looking for it As in the example we saw, we were looking for time, so we wanted an equation that had time in it. And what equation is the only one that has that in it, or can I solve for that and then plug it in another equation and so forth? With practice, you will get good at this.